So, in this lecture first I will discuss about an example on cantilever sheet pile in cohesive soil, and then I will discuss about the brace excavation. So, first I am giving an example on cantilever sheet pile in cohesive soil. Okay, I have solved one example problem on cantilever sheet pile in granular soil and anchor sheet pile in granular soil. Now, this class first I will solve one example problem on cantilever sheet pile in cohesive soil. Okay, so, I am taking the similar kind of example problem that I have solved during the granular soil. So, this is the dredge level, okay. This is dredge level, and this one is the ground level, okay. And the water table is here, which is 4 meter below the ground level. This height is 3 meter, okay. And the Cu here is 30 kilonewton per meter square, phi u is 0, and unit weight I am taking the same unit weight 9 kilonewton per meter cube below the water table, and above the water table again I am considering same Cu value above and below the water table. So, this is also 30 kilonewton per meter square, phi u is 0 degree, and above water table unit weight is 19 kilonewton per meter cube. Okay. So, this is the problem that I am taking. So, I am writing this value here, because I have to draw the diagram in this side. So, this is 19 kilonewton per meter cube. Okay. So, now first I will draw the diagram for different cases. So, as I mentioned that if I draw the diagram for the cantilever sheet pile wall in cohesive soil. So, if this is the dredge level, so this is the active earth pressure distribution, and this is also active earth pressure distribution. Okay. So, it is not in proper scale. So, actually this side will be more, this value. So, right hand side this value should be more, but I am writing this is Cu, this is the active earth pressure, and I am writing this is 2 Cu, and this value is, this one is gamma h minus 2 Cu, and this diagram is valid if phi u is equal to 0, that is K A equal to K P equal to 1. Okay. Then only this diagram is valid, and this value is gamma h plus d minus 2 Cu, and this value gamma d minus 2 Cu. This is active condition. So, what is H? H is this one, and this is D, and this value is again this smaller one 2 Cu. Okay. So, this is the active diagram. Similarly, the passive diagram will be same way I can draw. This is the passive pressure diagram. Okay. So, this is 2 Cu, this value will be gamma h plus d plus 2 Cu, this value is 2 Cu, this one gamma d plus 2 Cu, this value. Okay. So, this is the passive condition. So, and as I mentioned, there are 4 zones. So, suppose it is moving with respect to this height. So, the here it is active. So, this is the net diagram, here it is active, then it will go this side, and then this is the active diagram. Okay. This is the diagram. I am taking the only positive one, and this about this point, this is rotating. Since this oval is sheet pile is rotating about this point. Similarly, this that means this side is active, this side is passive, again this one active, this one passive. Okay. So, this side is passive. So, I can draw, this is also passive. So, my here diagram is this one, this is the passive pressure diagram. So, my net pressure diagram will be, the net pressure diagram will be this one. Then I have explained in the last class that you will shift here, then it will continue, and then it will again come this side, because here this portion is passive. So, it is more. So, the net pressure diagram will shift from this side to this side again, or right to left, again this right side in the bottom, this is the passive, which is more compared to active. So, again it will shift from left side to right side. So, the values are 2 Cu, and then this value is gamma h minus 2 Cu. Okay. So, this is the active gamma h minus 2 Cu, and this value is 4 Cu minus gamma h. Okay. And this value we have to add these things. So, it will come out 4 Cu plus gamma h. Okay. So, this is the net pressure diagram. Okay. So, this is the active case, this is the cantilever sheet pile in cohesive soil. But remember that this diagram is only valid if it is your phi u is equal to 0. Okay. Now, if phi u is not equal to 0 and C u is also not equal to 0. So, it is a C phi soil, then this diagram would be the similar pattern, only the value will change. Okay. So, this diagram would be in similar pattern. So, the values will be changed. So, in that case, I have to draw like this. Okay. So, this will again will be 2 Cu, because your Ka value in terms of Q, and Q is 0 here, and instead of this is gamma h minus 4 Cu. So, we have to write this is gamma h Ka minus 2 Cu. So, depending upon the position of this water table, it can be gamma dash also. Okay, minus 2 Cu, and this one again will be 4 Cu minus gamma h Ka. Okay. Again Kp part, this is starting point. So, this will not be Kp will not be there, because here in passive one the Q value is 0, and because your passive this Q starts from here, and here your value would be this point is 4 Cu plus gamma h plus Kp minus Ka into gamma d. Okay. So, here if it is your Kp equal to Ka equal to 1, then this part will 0, because that is the case. In case of here, where the phi value is equal to 0, 4 Cu plus gamma h, here 4 Cu plus gamma h plus Kp minus K into gamma d, because here this part will exist. Okay, so, this is the diagram. So, depending upon whether it is a C soil or C5 soil, you have to use this diagram. So, now what I am taking for our case, I am drawing the diagram, and our case it is your phi value is 0. So, you have to consider this diagram. Okay. So, now our case, first we will draw this diagram. So, and first we calculate that what is the value of H0. H0 means the no stress condition. Okay. So, what is the value of H0? Okay. So, that means the no tension crack depth. So, no tension crack depth H0 is 2 C by gamma root K A. Okay. Now, 2 C is 30 gamma, because here above the water table, because your H0 will be the above water table. So, it is 19 and Kp, this is root 1. So, this value is 3.2 meter. So, your H0 is 3.2 meter. Okay. So, I can draw this line, and this is 3.2 meter. Okay. This is the H0 no tension depth. So, this is 3.2 meter, and here at 4 meter I can write that this is your gamma into 4 minus 2 Cu. So, gamma is 19 into 4 minus 2 Cu is 30. So, this value is equal to 16 kilonewton per meter square, because at 4 meter it is, this is the 4 meter, gamma is 19 degree into 4, K is equal to 1 and minus 2 Cu, Cu is 30. Okay. Now, at dredge level, so now this will be another value due to the, actually this line will change the direction, because it is not linear, you know. So, because here water table effect is there, that is why it will give you a smaller value. Okay, remember that. So, that is why the total one here is, the total value at this point is 19 into 4 plus 3 into 9 minus 2 Cu into 30. So, this is equal to 43 kilonewton per meter square. Okay. So, this is 43, this is the total one is the 43. So, this is the total one is 43 kilonewton per meter square. Now, it will shift this direction, then up to this, then it will go this side. Okay. So, here this is 4 Cu minus gamma h. Now, here this gamma h value is, I can write this gamma h or q bar, which is equal to, gamma h will be 19 into 4 plus 9 into 3. Okay. So, this value is 103 kilonewton per meter square, because this gamma h we will use here, okay, or this is or. So, that means this value is 4 into 30 minus 103. So, this is equal to 17 kilonewton per meter square. Similarly, here this value is 4 Cu, this value is 4 Cu plus gamma h. So, 4 Cu is 4 into 30 plus gamma h, I have calculated 103. Okay. This is 4 Cu plus gamma h. So, this value is equal to 223 kilonewton per meter square. So, this is the total diagram. Now, I will solve. Okay. So, now I will solve this value. First, I will calculate the P A. Okay. So, P A I am considering only this portion, and this portion is 3.2. So, this height is 0.8, because up to this it is 4 meter and this portion is 3 meter. Okay. So, I am considering this portion as the P A. Okay. So, I am taking this is the P A value, and this value is this P A is y 1 bar from base of the dredge level, okay, from the dredge level. So, P A I am calculating, because there is 3 part, this upper triangle, this lower rectangle and lower triangle. Okay. So, P A is upper triangle half into 16 in 16, this is 16 into 0.8. Okay. This is the upper triangle, then lower rectangle 16 into 3, then the lower triangle half into 3, and this total is 43, and this rectangular dimension is 16. So, this is 43 minus 16. So, this 3 part will be 8.4 plus 48 plus 40.5. So, this is equal to 96.9 kilonewton per meter. Okay. And the y 1 bar I am calculating from this dredge level, and this is first upper triangle is 8.4, lever arm is 3 meter plus 1/3 of 0.8. This is 3 meter plus 1/3 of 0.8. Then the lower rectangle 48, that is 3 divided by 2. Then the lower triangle, which is 40.5 into 3 divided by 3, the total is 96.9. So, this is 1.44 meter. So, y 1 bar is 1.44 meter from the dredge level. Okay. So, now I will solve the expression. So, expression, the final expression was given for this type of problem was d square, where d is your this dimension. This dimension is, this is the d. Okay. So, the final expression we have d square into 4 Cu minus gamma h minus 2d P A minus P A 12 Cu y 1 bar plus P A divided by 2 Cu plus gamma h or gamma dash h, or sometime I can use gamma dash. Okay. So, that is equal to 0. This expression I have derived already in the previous class. So, the value I am writing, the d is unknown. So, d square 4 into 30, gamma h or gamma dash h I have calculated as 103. Okay. So, this is gamma dash h or gamma h or q bar is 103. So, this is 103 minus 2 into d, P A is 90, P A is 96.9 kilonewton per meter. So, this is 96.9 kilonewton per meter, minus 96.9 into 12 into 30, y 1 bar is 1.44 plus 96.9 divided by 202 into 30 plus again gamma dash or gamma dash h or gamma h is 103, that is equal to 0. So, after simplifying we will get 17 d square minus 193.8 d minus 365.80. So, after solving we will get d is equal to 13.05 meter and d provided is equal to 13.05 into 1.3, which is around 17 meter. Okay. So, after you can see that similar problem we have taken, and we have taken for granular soil, which is giving cantilever in granular soil, it is giving 9.5 meter, then cantilever in cohesive soil, it is given 17 meter, and the anchor sheet pile in granular soil, it is given 3.5 meter. So, here also 17 meter is very high value. So, you can reduce this value, you can provide the anchor sheet pile, or this soil is C value is very small, 30 kilonewton per meter square. If higher C value is there, so automatically for the higher C value this 4 Cu minus gamma h. So, this part will increase. So, the required depth will reduce. Okay. So, now there are there are few points. So, first point is that there may be some possibility that this, depending upon the Cu, this upper portion of the dredge level, the total stress can be negative. Okay. That means, the Cu H value, H0 value, if Cu value is very high, if Cu value is very high, so H0 can be greater than 7 meter also. So, if H0 value is greater than 7 meter, so upper portion we do not need to consider any stress, because we will not consider the negative one. So, this is one point. Another point is there may be one possibility that this 4 Cu minus gamma h, so gamma h is very high, Cu value is very less. So, it can go in this side also negative. Okay. So, in that case you may not use this sheet pile in that type of soil. Okay. So, you keep these things in mind before you solve this type of problem when you are designing the sheet pile. So, this is one thing, and the another thing is that when during the calculation of Hg, that of the anchor. So, I have used, so for the anchor design, anchored sheet pile. So, when I design the anchor, okay, so this is the anchor length and this is the ground surface. So, this is the H value, He value, and I give the expression He is equal to root over 2.67 into F, which is the anchor force F, and into S is the spacing into factor of safety, and then divided by Kp minus Ka into gamma into L. So, these meaning of these, all these notations are already been explained. So, in sometimes you may find that people are using the H instead of 2.67 they are using 2. Okay. So, but I would recommend you use the 2.67. Why they are using 2? Because people are considering, sometimes people consider this is the total active and the total passive force. So, that is why this is total one from the ground surface to the base, but I would recommend that you consider only this portion, okay, not the total one, because that is the stress is acting on this anchor plate. So, if you consider the total one from the ground surface to the base of the anchor plate, then you have to, instead of 2.67, it will be 2, but I would recommend you use the 2.67. Okay. So, that will increase the He value. So, you will get the more resistance. So, these are the points that I want to share with you. So, the next topic that I will start about the brace excavation. Okay. So, what is the brace excavation? So, brace excavation is that as you have observed that sometimes the depth of the sheet pile will increase if your height of the sheet pile is more. So, that means these sheet piles are used for the temporary construction like the excavation. So, this is one particular excavation site. Now, if your height of the excavation is very high or large, then only sheet pile is not sufficient. Okay. So, here also this figure you can see that this is the sheet pile. Okay. So, and if this height is very large, then only sheet pile is not sufficient, then the required depth of the sheet pile will also increase. So, to reduce that depth, and this for that type of problem, one bracing system is provided. So, that is called the brace excavation. What is the bracing system? This is the sheet pile. In addition to that, we will provide a beam. Okay. So, this is called the Euler beam or the well. Okay. So, this is the Euler beam. You see, this is the beam. This one is the beam which is connected with the sheet pile wall. This is sheet pile wall, and then we provide some lateral support. So, this is the lateral support. These are called the strut. This is called strut. Okay. So, here you have the section. This is the sheet pile wall. This is the sheet pile wall. Then this is the Euler beam. This is the section of the Euler beam. Okay. And this is the strut. So, this is the strut. So, you can see the strut has two spacing. One is vertically. So, there is one spacing. This is in terms of vertical. Okay. So, this is vertical. Another one is the horizontal. Okay. So, this is the SV, this is the SH or the horizontal spacing. So, that means when you design this thing, you will find you will use this SH, and we can provide the SB also. There can be the one level start, two level start. Here there is a 4 starts. Okay. And there is the spacing between the respective starts. So, what are the things when you design? So, we have to design what are the force is acting on this strut, because here the wall will deform and this side also deform. So, there will be axial force will be developed in the strut. So, the strut will carry the axial force that we have to determine. So, this beam, what is the, these beams are carrying what is the moment coming on this beam or the maximum moment. So, that also we will calculate, and what is the maximum moment is coming on the wall. Okay. Coming on the wall. So, these three things we will determine. Okay. So, during the design, fine. So, now to determine these things, so determine these values, some guidelines are suggested. Okay. So, here the earth pressure equation or the distribution pattern is suggested by Peck, Hansen and Thorburn. Okay, 1974. So, what they have suggested, because here that distribution depends on many factors. Okay. What are those factors? Because here this is not a wall, in between the axial support or the strut there. So, that depends on the spacing between the starts. So, that depends the construction time. Okay. So, rate of construction, depending upon all these things or keeping all these things in mind, based on the observation, they have proposed this type of distribution for different types of soil. So, if it is sandy soil, so this is the distribution or this is the value of the P A. Okay. So, this is the P A, value of the P A, or it is equal to 0.65 gamma H into K A, or where K A is equal to 1 minus sin phi divided 1 plus sin phi, or this is tan square 45 degree minus phi by 2. So, if this is a sandy soil, if it is a steep clay, then steep clay, if this value is gamma into H minus C is Cu is less than equal to 4, then you will use this distribution. So, this distribution is 0.2 gamma H to 0.4 gamma H. Okay. So, this is the value, and if this is the soft to medium clay, this value is gamma H divided by C is greater than 4, then we will use this distribution. So, this is the P A value is gamma H minus 4 Cu. This is the P A value, okay, 0.42. So, to gamma H to 0.4 gamma H, or we can take average value of P A is equal to 0.3 gamma H, because this is the average value. So, these distribution will help us to design the start force or to calculate the start force, bending moment coming on the wall and the bending moment coming on the beam. Okay. So, based on this this is the simplified approximate method by which we can determine those things. Okay. So, I will discuss this value with a problem, and in the next class that how we will determine the axial force and bending moment of a base excavation which is constructed in either clay or sand. Thank you.